Hello everyone, I am Sarthak.
I'm Siddharth.
We are PhD students in Electrical Engineering, Columbia University, New York.
Today we'll be talking to you about the filterless Class D amplifier that we designed as part of the VLSI Design Lab offered by Professor Peter Kinget in the spring of 2014. I'll now be talking to you about the overview of the design of our chip. But before we get to that, I would like to give a brief background about the operation of Class D amplifiers. As opposed to Class A or Class B amplifiers, where the transistors in the output stage are used as small signal amplifiers, the output stage in a Class D amplifier uses the transistors as switches. The block level overview of the system is shown in this figure. The input comes in from the left and passes through a single-ended to differential converter, which generates two outputs. The first output is exactly in phase with the input, whereas the second output is exactly out of phase with the input. Both of these outputs pass through two channels that are same in all respects to each other. The most important part to the operation of a Class D amplifier is the PWM block. PWM stands for pulse width modulation. This block generates a high frequency pulse whose duty cycle is directly proportional to the instantaneous amplitude of the input. The output driver consists of the switches which connect the load to either the supply or to the ground. The integrator is necessary for the closed loop operation. This is the PCB that we designed, which contains the peripheral circuits that we need to demonstrate the functioning of our chip. This is our chip right in the middle. To the left we have the batteries which act as a power source for the PCB and for the chip. This is the input to the PCB and to our chip, which is a standard 3.5mm jack. An iPhone or any other audio source can be attached to this input. This is the speaker which acts as the output through which you can listen to the audio signals. And this is the volume control knob that controls the volume of the entire system.
This is the PCB and this is our measurement setup. The input comes here and goes to the PCB, goes to the chip, and we are probing the differential output of the chip which are taken into the oscilloscope. Channel 1 and channel 2 denote the two differential output waveforms. Both of them have 50% duty cycle. Next we apply input. We can see there is a modulation in the two waveforms, and if we increase the volume knob, the modulation changes. Next we see the differential waveform. We can see that this shows the ternary scheme where we have three output levels: positive, 0 and negative level.
This is a demo of the working of our chip. First up we have Roar by Katy Perry. Next up we have Chak De India, a Hindi song. And finally we have the most popular song on YouTube. As you can see, as I change the volume control knob, the sound level changes. We'd like to thank Columbia University for giving us the resources to design this chip, and to Moses for helping us fabricate this chip.
Thanks for watching this video.
If you want to learn more details about our project, please check out the project website linked in the description.
If you have any feedback, do leave them in the comments below.